Alrighty, so far we learned about what a sequence is and also how you can systematically generate multiple sequences from a single proof obligation. For example, the proof obligation for invariant preservation, depending on how many events and also how many invariant conditions you have. And we also learned about in the last part what the inference rule is, especially its syntax, its meaning, and also its connection to sequence. And we kind of gave you the explanation about it really boils down into like a nested implications whenever you want to apply an inference rule. And we'll now be ready to really try to see how we can prove any outstanding sequence that has been generated from some proof obligation. And the proving itself is a very creative process, as you can see from maybe your previous math course like an EECS3342. So the best I can do is to just give you the general guidance about what steps you should really take, and also to show you some example with a conforming structure. That's the best I can do. But of course, you should definitely study the example that we're still going to do throughout the course, and possibly we can do some extra exercises as well. That'll be the best way to train you to really do proofs. All right, let's now do a quick example first of all. Okay, let's say this is one of the sequence that we generated from the proof obligation for invariant preservation, right? Just recall very quickly. It's about invariant preservation, INV, and specifically for invariant condition number 1 for our initial model, model 0. And it's relevant to events in and out. Remember, we also got 3 other sequence that's related to this particular invariant preservation or proof obligation, right? But we're going to talk about them in a moment. Okay, let's say this currently is outstanding, meaning that we haven't really proved that yet. We want to say that we want to prove that n plus 1 is actually a natural number, assuming that d is a natural number, n is a natural number, and n is less than or equal to d, right? You just remember for this particular sequence, different parts come from different parts in your in our model, which I explained in detail earlier. If you got any doubts about how this particular sequence is formulated, you should definitely refer to the earlier part. That's something I assume for now. Right? So what will be the general steps? There are 2 things over here, right? So number 1, given the outstanding sequence, you want to apply a single inference rule that's applicable. And that particular inference rule is going to transform some that particular outstanding sequence into one or more, depending on the rule itself, right? It could be, remember in the antecedents part for the inference rule, we said there might be a set of sequence over there, but the consequence will just be a single sequence. But we'll talk about it, okay? And you may just turn out to really get more sequence to be proved instead. But typically, this transformation process eventually can really branch out to many sequence. But you want to make sure every branch over there will turn out to be axiom ultimately. So that's why the second step will be you want to keep applying the inference rule until all the transformed sequence are axioms. Well, basically, if you can apply the inference rule where the antecedent part is simply just missing, right? If you remember the example we did, let me show it to you. For example, if the sequence itself can be reduced to this particular sequence over here, in which case the antecedents is simply just missing, meaning that whatever you have over here is automatically proved without any further justification. That's our goal. But if you only reduce your sequence into this particular, let's say, form over here, in that case, in this particular form, in that case, you still need some further justification, right? That's something we have to see. All right, let me go back. And let's now talk about one example, right? How do we conduct a formal proof for this particular sequence? Let's take a look, okay? Let's just get the context very clear. We got some outstanding sequence to prove. Over here is outstanding, right? So that's the sequence that I just refer you to, right? You should definitely review about how this sequence is generated in the first place, which we spoke about earlier, with respect to the invariance proof obligation rule. And I can tell you that in order to prove this particular sequence, it would be sufficient to use these 2 rules. Of course, the order of applying the inference rule will be so important. All right, so let me just, you can now pause the video and think about how you may apply these 2 rules. should you apply this one first or should you apply this one first? But we may not have to use both of them. Maybe just one of them will be sufficient, right? You can now pause the video and think about it. All right, assuming that you thought about it, so I would suggest we start with this particular outstanding sequence over here. I'm kind of following the notation in the textbook. So when you do the reading, you will see consistency, right? So that's what we start with. Question number 1. Can we actually apply this particular inference rule to transform this particular sequence? The answer is no, because you can see that in order to apply this inference rule, that means this is something that we this is actually the sequence that we actually want to this is a sequence that really has to map, right? But somehow you can see n plus 1 is a member of natural number. This one match. However, you can see this part over here is n is a member of natural number. So that's the rule, what the rule requires. But not only that you got n is a member of n, you got also 2 extras over here. So that's not really matching the rule. So you cannot apply this. You just cannot, right? Hopefully that's making sense, right? Let me say that again. The inference rule is saying that if you have a sequence of this form exactly, in that case, you can claim that it's automatically proved without any further justification because the antecedent is empty. However, in the sequence that's outstanding over here, let's try to do some matching over here. This part here, this part over here matches the rule. However, this part here does not exactly match. To be more precise, this part here is more like a superset of this one over here because we got not only this, but we also got 2 extra predicates over here. So that's why we cannot apply that, maybe not just yet. So it turns out this monotonicity rule is very, very useful. What does it really say? Let's review it again. It is saying that if you want to prove this particular sequence, where the sequence got some goal and also maybe multiple hypotheses, it would be sufficient to prove the same goal under the assumption of less hypothesis, right? So for example here, if I want to prove this particular sequence, it has a goal over here. It has 3 predicates as the hypothesis. It would be sufficient for me to prove the same sequence, the same goal, but under less hypothesis. For example, I can only choose the one that would be sufficient for me to conduct the proof. Well, what should I choose? Well, since I know, you can see this part here is already matching this part here. So all I need would be exactly this. And this is really appearing over here. So that means the other 2 can just be dropped, right? So I'm really, you can think about this one over here is really the H1 I want to keep. However, these 2 are really the H2, which I want to drop, right? That's some insight for you about how to apply the rule. Let's now do it. So I'm just going to do this. So I'm going to say I'm going to transform this outstanding sequence into another one by applying the monotonicity rule. So I'm saying mon over here. After this, I should really get just another sequence, right? You can think about this is somehow matching this, and then it would be sufficient to prove this one instead. Well, so to be more precise, you can think about this part over here is H1. This part over here is really H1. And these 2 over here is really H2. These 2 over here. So these are really H2. So I'm going to drop H2, right? You can see to prove this, it will be sufficient to prove it where H2 is dropped, right? So how should we write it? The way to write it would be, let's now also go back to here, right? I'm going to drop the H2. So that will be only n is a member of the natural number, right? So that's the hypothesis, just 1. So now I'm getting less hypothesis. And also n plus 1 is a member of n over here, right? It's so important for you to see how we can actually apply the rule of monotonicity on this particular sequence, and we generate just another sequence, okay? So what we are saying over here is, let me just say it again, it's really important to always recall the meaning for inference rule. The inference rule is basically saying that to prove the original outstanding sequence it is sufficient to prove this instead. To prove this instead. Right? It's so important, right? And you may, in a general structure of the proof, you may have to apply multiple inference rule to really transform into different sequence. It's kind of like a tree structure. All right. To prove the original one, it would be sufficient to prove this one instead. And are we done? Well, we're basically done, because now we can claim that we are now we don't need any further justification, because based on another inference rule over here, you can see the goal of the sequence over here in the consequent is actually n plus 1 is a member of n, is a matching. And also the hypothesis is actually n is a natural number, right? So this is matching exactly this. So we can simply claim that this is already proved without any further justification, because the antecedent of this inference rule is missing, right? And all we got to do is to make sure we can now claim that this sequence is proved by using P2, right? So that'll be one single proof to conduct, right? And any other proof that we're going to do later, when we go back to other parts of the model, it will be very similar. And I definitely should really leave time for you to do exercises. But just make sure you understand the steps and also the structure, and also about the pattern matching, which I explained before, especially how this one here can match this rule over here, right? Oh, more precisely, how these two sequence over here, how this sequence here can match this guy over here, the consequent, and how this one over here can match the antecedents for this inference rule is so important, right? Let me just say one more thing, right? Can think about this is the antecedents, and of course this is a consequence, right? Think about how this is matching the consequence and how this one here is matching the antecedents specifically. All right, let me go back. And that's a formal proof I just showed to you on the iPad, right? So now you can just go over this again.